I want to begin by telling you a little story. Maybe I should tell you a little bit about ourselves. I'm from Toronto, Dave is from Montreal, and Gordon is half Canadian. So it's almost a perfect panel to have here today. I graduated from university in 1996, and that summer I went down to visit my brother, who was living in Chile. And one weekend, we drove out to the beach. We drove from Santiago out to the coast to spend the weekend, and my brother bought what everybody in Chile knew was a great piece of beef, which was a steak from Argentina over the border. It had to be good because for people in Chile to say the stuff from Argentina is better, it really is better. So we made a fire and we roasted this big hunk of beef over these coals, and it was literally a life-changing experience. I put this steak in my mouth, and I asked what was both the simplest question and what would turn out to be the deepest question, which is, why does this taste so good? That led to my first book, Steak, in which I literally traveled around the world searching for the best piece of beef. But what it really did was lead to more questions. We all love food. We are all in search of delicious food, but we never really asked the big question, why is it delicious? Well, then when you start to think about steak, you start to look at, why do cows eat what they eat? Why do they think it's delicious? What is flavor? And where is flavor? When I ate that steak, was the flavor in the steak? Or was it about a brain experience, what was going on in my mind? If it changed the course of my life, it had to be mental. So those are the questions I want you to think about, and hopefully some of them we will resolve or at least explore as we begin, and we're going to start with Gordon Shepard.
So thanks very much, Mark. It's a pleasure to thank the organizers also for the invitation to participate in this really exciting program. The subject of my remarks will be how the brain creates flavor and why it matters. And this is based on a hypothesis. And the hypothesis is the flavor isn't in the food, flavor is created by the brain. The more we know about the brain, the more we can know about flavor. In the spirit of our session of taste and storytelling, I'll tell 4 stories, very briefly, about how the brain creates flavor. So first, how retronasal smell and flavor drove human evolution. So in our daily experience of flavor, we don't usually think much about evolution, but in fact, in the famous quote by Theodore Dostoevsky, nothing in biology makes sense except in the light of evolution. It turns out that flavor is no exception. We're mammals, which began to evolve from reptilian ancestors some 250 million years ago. You can see on the far right there a magnocodon, which was one of the early mammals. Tim Rowe, a leading paleontologist, used X-ray tomography to look at the endocraniums, the insides of the craniums of early mammalian fossil skulls, and found he could identify the outline of the olfactory bulb and olfactory cortex in the lateral cerebral wall. Now I need the pointer, I guess. Didn't realize we don't have that. Great. So just by looking at the inside of the bone case, he could see that the frontal lobes of these very early mammals had a large olfactory bulb and a large olfactory cortex.
English psychologist,
and practically no neocortex. He noted that successive pulses of enlargement in successive fossil species were correlated with a large expansion of olfactory receptors. So counterintuitively, mammals began to be dominated by their olfactory brains, in which the new neocortex had to, as it were, elbow its way in to an already very large olfactory basis. Subsequent evolution brought about the enhancement of the neocortex in the many species we recognize today, but the olfactory part has remained as the base. So in parallel with a large family of olfactory receptors and a large olfactory brain, the early mammals had something else. they acquired a hard palate separating the mouth. Where's that? Where's the... Having a problem running this thing. The hard palate is there, separating the mouth and the nose. And that meant that when food was in the mouth, it could release volatiles which were carried by retronasal smell, breathing out into the nasal cavity, and therefore bring about an enhanced appreciation, sensation of the odors that were arising from the food in the mouth. This allowed them not only to smell what was outside by sniffing in, orthonasal smell, but also smell the food in their mouth by breathing out. As we've heard from Charles Spence, retronasal smell is a very important part of our appreciation of flavor, combined with all the other senses to make a multimodal flavor perception that he is the acknowledged world expert in. We may hypothesize that flavor enhanced the choosing and consumption of healthy foods in mammalian evolution. We may further hypothesize that it played an even more important role in human evolution. Richard Wrangham has summarized his long-term studies of the diets of early humans in Catching Fire, a wonderful book, How Cooking Made Us Human, providing evidence that the early control of fire, starting with pre-humans enabling cooking of food to play a key role in increasing the intake of high-energy foods from the cooked foods, which in turn fueled the explosive growth of the pre-human and human brain, accompanied by the growth of the social interactions that occurred around not the family dining table, but the family hearth, which I'm sure David Howe will tell us much more about as providing the bonds and the clue that were crucial for the evolution of human societies. The strong growth of the brain is shown in this next graph, which shows that over 2 million years, the brain increased strongly initially and also strongly then over that period of time, and even more strongly in Homo sapiens. This is sobering, I think, that there might have been a much diminished human brain if not for retronasal smell and flavor, which attracted humans to the food that was the basis, the nutritious basis for the great growth of the brain. Maybe we can discuss that also further. A key point for our story is that the olfactory bulb and cortex didn't get smaller during evolution, even though they look small here. The brains got bigger. The olfactory part stayed about the same, but the brains got much bigger, and they remained, brought about a tremendous enhancement of the flavor experience in humans. And I think our symposium is going to show that. So the next story then uses wine tasting to exemplify this enhancement that occurs, of flavor that occurs in humans. So if neurogastronomy is how the brain creates the flavor of food, then neuroenology, and I apologize for this term, which some people might feel was unnecessary, must be how the brain creates the flavor of wine. Wine tasting provides an excellent example of applying the principles of how the brain creates flavor, because it's a food that consists almost entirely of flavor-producing components. Here's a diagram of the moment of taking a sip of wine into the anterior part of the mouth, activating the touch, taste, and olfactory systems, providing the main inputs that usually drive flavor, But also not shown here will be the sound even of taking up the wine, and also further in moving it, manipulating it, and swallowing it, as well as the visual system, which plays an enormous part in anticipating what our experience is going to be in taking up the wine. We not only eat with our eyes, but we drink with our eyes. So this diagram then shows both the peripheral systems feeding in to the brain, but also I've made an attempt here to summarize some of the many parts of the brain, the central part of the brain, that are involved in decision-making, in action, in reward, in integration of the inputs, in assessing value, and creating emotion, as well as it wasn't even placed to show the vast memory systems that also play an enormous role in creating flavor. This is all based on the work of Ed Rolls and Morton Kringelbach and many others, including systems for learning and memory. It supports the claim that the perception of flavor engages more of the brain than any other human behavior. I hope that also will be a subject for discussion. No wonder it played a role in human evolution. So retronasal smell is dominant in wine tasting, but little is known about the airway dynamics. We've carried out a first study with a model based on the human airway and constructed by fluid dynamics engineers that has suggested that with wine in the mouth, there's a pooling of the volatiles at the back of the mouth that are carried out, up into the nasal cavity by retronasal airflow, whereas when we breathe in, the air currents tend to go past this pooling and not be carried into the lung. So there's very little known about airway dynamics, and we hope this will be a first step in understanding the actual mechanisms of retronasal smell. Swallowing then coats the oropharynx with a coating of the wine so that when breathing out, the air carries a large density of volatiles that have been on the pharyngeal wall, giving the aroma burst with retronasal smell that provides the strongest stimulation of the so-called taste of wine. So we thus have a dual olfactory system, which Tim Rowe and I have called ortho-retronasal olfaction. Not very imaginative, but the idea is that we should refer to the system not just as smell, because people all think of that smell then almost exclusively of breathing in, but rather that it's both ortho and retronasal olfaction. We owe a huge debt to Paul Rosen. It's a special pleasure to have him here for rediscovering the system decades ago. Our studies support his hypothesis that the two subsystems give rise to distinctly different aspects of smell perceptions, which I'm sure we'll hear more about from him. So the third story is how the brain creates images of smell, flavor, and desire. We've seen that science can tell us what brain systems are involved in creating smell and flavor, but we still want to know how they work. So in the next slide, we know that odor molecules activate a protein called an olfactory receptor, 7 transmembrane domains, that activates the receptor to set up impulses, which then travel in subsets of neurons expressing the same receptor to a particular target called an olfactory glomerulus, in the olfactory bulb. And different receptors characterizing different subsets then go to different glomeruli, so that in total a map is formed, a pattern is formed on the olfactory bulb of the glomeruli activated by a particular odor, and you can open out this surface of the bulb to make a map, two-dimensional map, showing with, in this case, with 3 odor molecules that differ just by 1 carbon and its hydrogens, that you get similar patterns, but they're different enough so that you can distinctly pick them out as different. And there's an analogous process in taste receptors that maybe Ola Morrison will tell us about at the periphery. So thousands of cells expressing the same receptors then can create a pattern of activated glomeruli that represents the stimulating molecules. We call this a spatial pattern an image of the odor molecules, a virtual odor image. Just like a visual image, it also varies over time as well. So this brings smell directly in line with other systems. We know that the body surface is represented in the brain by a pattern of stimulation. And we know that the auditory system represents sounds also by a map of the different frequencies here in the cat, and even more complex in the bat. The brain is very good at recognizing these images, but as we shall see, has great difficulty in describing these complex patterns in words. The olfactory images are stored in microcircuits that are similar to those in the hippocampus, here in the olfactory cortex, in the hippocampus, basically the very similar architecture. The hippocampus, of course, being involved in higher cognitive functions, such as learning and memory. The olfactory cortex, then, is not just a sensory processing stage, it's actually a higher cognitive center for learning and memory. The olfactory system we're learning is a very powerful system, very close to the periphery, so that it begins working immediately on very higher cognitive processing of the olfactory input. So, the last story, the brain creates the aesthetics of smell and flavor images and language. And if I haven't been provocative up to now, I certainly hope I am at this stage. So how might these brain mechanisms give us insight into the aesthetics of smell and flavor? So I'll stick my neck out just to stimulate the discussion. So I think we all know this painting by Van Gogh. Smell and flavor are often compared unfavorably to vision when it comes to describing the perception in words. This seems self-evident in the case of a depiction of a visual object, such as Van Gogh's sunflowers. These are obviously sunflowers, and this gives us the conviction that vision is directly connected to words, whereas olfaction and flavor have very poor connections to words in describing them. But remember now, I've said that the olfactory stimulus is represented by a pattern, and the pattern is virtually equivalent to a visual image, so that we're actually dealing with an image. So let's see what happens to visual images if they get complicated. So here's abstract art, however, that tests that simple idea. This is a painting by Cy Twombly. A critic has written that Twombly's art has always, quotes, always been elusive, and for many people, even enthusiasts of contemporary art, unfathomable. Twombly himself has maintained an unusual reticence, as in the following statement: to paint involves a certain crisis. This doesn't seem like what Van Gogh felt in depicting a sunflower. A certain crisis. It should by no means be limited to a morbid state, but could just as well be one ecstatic impulse. So this visual object seems as difficult to describe in words as wine. Humans are quick to discriminate patterns, but are slow to describe them quantitatively or with language. So these two faces are another example of visual images. So they're quickly identifiable, and I assume that everyone can tell which one is male and which one is female. Should we have a vote? So how about the one on your left? Male or female? And the one on the right? Female. It was a very tentative response to this. So humans are quick to discriminate patterns, but are slow to describe in language. These two faces are quickly identifiable as male and female, but the differences are difficult to describe in words. So if you had only one of these, and there was a room full of guys, and you had to go in, and maybe just a few women, and you had to identify them, sort them, it would be from being instructed by what the slight differences are, you would have trouble, I think, in actually carrying that out. So these differences, difficult to describe in words, are true of faces, and the irregular patterns I showed you of activation in the olfactory system are equivalent to these complex patterns that we see in faces. Similarly, in music, we have this explanation of the perception of music by the great conductor Bruno Walter. Music springs from and is replenished by a hidden source which lies outside the world or reality. Music ever spoke to me of a mysterious world beyond, which moved my heart deeply and eloquently intimated its transcendental nature. So I'm going to replace music here and music here with wine. So how many times have you heard wine described as springing from and replenished by a hidden source lying outside the world or reality? Ever spoke to me of mysterious worlds beyond, moving my heart deeply, etc., etc. So these are attempts to describe, again, patterns that are so deeply embedded that they defy the ability to put words on them, even though we think that music is a simple sense to be able to describe in words. And finally, here's one of my favorite quotes from T.S. Eliot: "Music heard so deeply that it is not heard at all, but you are the music while the music lasts." So maybe as we leave our symposium, flavor sensed so deeply that it's not sensed at all, but you are the flavor while the flavor lasts. So with that, I leave you with the questions of how this gives us insight. These brain mechanisms give us insight into not only the sensory perception of flavor, but also these deeper feelings that come about from a system that has played an incredibly important role in human evolution and that is driving us still today. Thank you.